Good afternoon, students. This is the lecture for Wednesday, November 15th, 2023 of Computer Science 201, Section 60 in the fall 2023 semester. In today's lecture, we will follow up on Monday's lecture where we introduced the topics of searching and sorting. This lecture follows on that and illustrates some of the concepts in code, and we also measure some properties of the code that we're talking about. Before we go too much farther, remember that the administrative note is Project 2 is due next Monday night. I will put out more videos later this week to help you with that if you have any questions. If you have any questions, feel free to send them to me. I will get to them when I can. A quick reminder, why do we worry about sorting and searching? Well, we mostly worry about searching, as you've seen with things like Google and Yahoo and Bing and a number of other tools. Searching is a problem that happens all the time in computer science. We do a lot of searching of data. On Monday, we covered two algorithms for searching, linear search and binary search. And things that's important to remember are that linear search is always guaranteed to work. Basically, it will find the item we're looking for if it's in the list, and if it's not in the list, it'll tell us truthfully it's not in the list. But it's very inefficient. Linear search, you start from the first element in the list and compare it to your target, and you continue through every element in the list until you either find what you're looking for or you have looked at every element and you're now convinced the one you're looking for is not there. So linear search is useful, but not really useful in that sense. Binary search is much better. In binary search, if the list is sorted in proper order, for say increasing the smallest element first and the largest element last, then we can use a technique essentially of going through a balanced tree. We go to the middle element in the list and check to see if that's our target, and if not, is our target greater or less. Based on what we find, we can throw half the list away right then. We don't have to look anymore. If we're looking for something that's less than the midpoint, we can throw everything greater than the midpoint away. So because we can throw half the list away every time, binary searching is more important. So anytime we want to do binary searching rather than linear searching. However, while linear searching works on all lists, binary searching only works on sorted lists. And so that indeed makes sorting a very, very important problem in computer science. Typically what we'll have is we will pay the price to sort a large list of data, say once per day or once per week or on rare occasion. And then we can search for it millions and millions of times. But we still want to find a fast, efficient way to sort because it is a hard problem and it could take us much time. So the focus of today's lectures, I'm not going to go through linear and binary searching again like I did on Monday because they're fairly straightforward. We will talk about a little bit when we get to after Thanksgiving. For now, what I'm going to do is I'm going to look at the algorithms I talked about on Monday, and I'm going to instrument them, and I'm going to run them. The GitHub repo under code samples has a file called November15thcoding.py. That is the code that I use in this lecture. It's already been posted ahead of time. You can get there, and you can play with it yourself, see how it works on your computer, see what different results you get. In that code, I've implemented both bubble sort and selection sort using the iterative versions of the algorithms. They're just not intuitively recursive. As I mentioned on Monday, you can implement them recursively, but we generally don't. We just do it iteratively. When I execute bubble sort and selection sort, I'm going to count the number of comparisons required to sort a list. I'm going to count the number of times I have to swap values in the list to get the list sorted. And I'm going to measure the amount of time in seconds it took my computer to sort that list. Emphasis on my computer. you can run this exact same file on your computer and you will get slightly different results. You'll get the same results as to which is more efficient in terms of comparisons and swaps, and relatively the times will be about the same. But I'm using an 8-year-old Mac. It's not the fastest computer anymore, so your computer probably would solve the same problem a little faster than me. That's not a huge issue. The huge issue is that, roughly speaking, the differences in time between the three algorithms are going to be the same. So I'm going to measure comparison swaps in time in seconds to do bubble sort and selection sort. Now, I have implemented quicksort using a recursive version of the algorithm because, as I mentioned on Monday, it's just naturally a recursive algorithm. It just naturally lends itself to recursion. We start with a list. We take roughly half the list. We take roughly half of that list. We take roughly half of that list. We keep going. We call ourselves. When you have a recursive function, what is important to count, since recursions are fairly expensive, as we mentioned before, how many times exactly do I have to recursively call the quicksort algorithm? So I'm going to count the number of recursions, and I am going to count the number of times I have to compare two values in the list to each other. In the recursive implementation of quicksort, you don't really swap elements in the list. You simply move them to one place or another. I'm not going to count swaps, therefore, because of the algorithm. It would not make a huge difference if I did. So that's what I'm going to do with this code. Now, with that, let's switch to PyChart. And as I mentioned, this is the code that's on the GitHub repo already. I'll quickly go through it, what I've got here. I import the random library. This is what I'm going to use to generate the random numbers in the function that does that. We'll talk about that in a second. I also import the time library. Python comes with a variety of functions that can be used to measure time in seconds or whatever other unit you prefer. I'm going to use that to count the time in seconds various things take. Okay. First, you'll see the bubble sort iterative function. It takes a list. At the beginning of the function, I count the number of comparisons and the number of swaps, and then I run the bubble sort algorithm. For each iteration of the algorithm, I go from the beginning to that part of the list that is not sorted. This range right here indicates just the unsorted or not yet sorted part of the list. Anything beyond this, from length minus I minus 1 to the end, is already sorted, already the proper order. I don't need to deal with that. Okay? The largest values have already bubbled out there. So when I'm in this loop, okay, every time I make a comparison, every time I'm going to increment my comparisons by 1, and then I'm going to directly make my comparison. I'm going to compare j to j plus 1. Now, the j to j plus 1 is why I use the minus 1 in my range. Otherwise, I'd get an index out of range error. If you don't want to use the minus 1 here, you'd have to change this to be j minus 1 and j. It's no big deal. Anyway, I do this comparison. If it is true that the two numbers are out of order, so in other words, something like if I have 6 and I have 5, then I have to swap them. Okay, and so I will increment the number of times I swap values, and I use the same method I used in class on Monday to swap the two values in the list. There are other functions you could use that might be slightly more efficient, that might save you a nanosecond or a millisecond here. We're not going to worry about that. This is just a simple way to swap the two things. And again, you can see I'm counting the number of comparisons, and I'm counting the number of swaps. At the end of my function, I'm going to print out the results in terms of how many comparisons did I make and how many swaps did I make before I return my sorted list. I said that this inner loop is one time through, so to sort the entire list from beginning to end, I have to embed that all in an outer loop. The outer loop does the inner loop for every value. So This is what sorts the list. This is going to print out my measurements, and I'm going to return the sorted list when I'm done. That is the iterative list. That is the iterative implementation of bubble sort. Now, I mentioned also I had the iterative version of selection sort, which you see here. I have a list of numbers, a list of integers that I take in. I'm going to return the list sorted in order. I'm going to, again, count the number of comparisons and then some swaps. So I start with them. I start with the comparisons to swaps equal to 0, and then I go through the algorithm. Just like with bubble sort, I have an inner loop, an inner for loop, that executes once that says, let's find the smallest value in the list. And it go through, and I add a comparison every time I compare two numbers to see, is this the smallest, is this the smallest? And I keep track of the smallest value. When this loop ends, the value smallest is the index in the list of the smallest number. Now, if that is not equal to I, and let me fix, if that is not equal to the first instance in the list, then I have to swap. Okay, so the smallest is not first, I have to swap. If the smallest is the first, I don't need to swap. Okay, and this is how I swap the two values. And again, this inner loop is embedded in an outer loop that runs from the beginning all the way through to the end and gets me to the smallest. Okay, so that's the loop. And again, at the end of the loop, I print out my results, how many comparisons and how many swaps, and I return the list of numbers. Now, quicksort is recursive, and I will acknowledge up front, for simplicity in presenting my results, remember, I'm comparing how many total comparisons it took and how much time it took and how many recursive function calls I had. I chose to sort of cheat and use global variables. Okay. I know we said not to, and there's lots of reasons, and test 2 had a lot of questions about why not to use them. But just for simplicity in explaining this, I use two global variables, calls and comps, that compare, that keep track of how many times I call the function recursively and how many actual comparisons I have to make to solve the problem. This is the code, other than the instrumentation, this is the code I used in class on Monday. It's in Monday's lecture, and it's all there. The idea is I take a list, I pick an element at random, in this case the first, to be the pivot point. I create 3 lists, everything that is the pivot that's equal, everything that's less, and everything that's greater. I go through the list once, comparing each item to decide whether I put it in less, equal, or greater. And then I take my equal and I put it in the middle between quicksort results from less and quicksort results from greater, and I return the results. Now again, because this is recursive, the method I used for the iterative, where I printed out my results in the actual function, will not work, so I've done that in the main program. I have a helper function here that I've defined that creates the list of my list of random numbers. This is what I showed on the Monday lecture in the main program. I put it as a helper function. I start with an empty list of numbers. I get input from the user, how many numbers do you want in the list? And for that number, I generate a random list of numbers from 1 to 1 million, and I return that. So the main program, the first thing I do is I generate my list of numbers. That's the function up above. That's the helper function. This is going to generate my random list of numbers between 1 and 1 million. Now, I want to use the same list to compare directly the exact same list of random numbers, the performance of bubble sort, selection sort, and quicksort. Lists are mutable. If I take my random list and I give it to bubble sort, and bubble sort gives me back a sorted list, guess what? I no longer have my random list. I cannot directly compare the results on that same list with quicksort and selection sort. So what I'm going to do next is make 2 more copies for a total of 3 copies of the same list. The reason I'm going to do that, the reason I have this code right here, is so that I will have 3 independent copies of the same randomly generated list. I can have each of my 3 functions, bubble sort, quicksort, selection sort that same random list, and I can get a fair comparison among the 3 of them. I don't have the case, if I were not being careful, because lists are mutable, because the first function, bubble sort, will sort the list, I would then be giving selection sort and quicksort already sorted lists, which is not something we want to have happen to assignment. So all this code does, all these 5 lines do, is they make 2 more copies of the list, so I have 3 identical copies. I can make a fair one. All right, let's call bubble sort first. So I'm going to call bubble sort with one of my 3 copies. I'm going to use the original list of nums with bubble sort. And I'm going to time how long it takes. I'm going to call my function. Remember, I imported time at the beginning of this, and there is a function time in the module time. So it's time.time is a function that gives me the current time as the computer understands it in seconds. How exactly the computer understands it will vary. I don't care about that. I'm just going to care about elapsed time. So the time when I start goes in a variable called bubble start. Then I call my function. Then I call time.time again and get bubble end. And what I'm going to do is take bubble end minus bubble start, and it's going to tell me in seconds how long it took bubble sort to sort this list into the proper order. Fair statement, this is not perfectly pure, because there's a little bit of overhead in invoking the function, there's a little bit of overhead in returning from the function, but I'm going to be consistent about it, and this is close enough. You'll get the idea. Okay. But that's why I put the time down here rather than up in the function itself. So I'm going to get one set of results. Then I'm going to call selection sort with a second copy of the list. The reason I do this is list, same random list I started with. I made a second copy so bubble sort doesn't ruin me. Again, I'm going to call time.time before I start. I'm going to call time.time after I end. The difference between those 2 times, between line 128 and 126, that's how long it took in seconds. And again, not pure because of the overhead starting up the function, but again, I'm consistent in comparing among the 3, so this is very useful. I do print out the list of variables so you can see that they are indeed working as sorted. Then I call quicksort. Now I mentioned, because quicksort is recursive and I want to count the number of recursive calls I make, I'm going to cheat and use these 2 global variables to make the count work. Okay, I'm going to define the global variables here. I'm going to increment them in the function. No matter how many recursions deep I am, I can increment where I should. I can count properly. I am going to record time exactly the same as I did with the iterative functions. Okay. I'm going to call time.time to start. I'm going to call time.time at the end, and the difference is going to be how long it took to sort these numbers. Again, I'm using a 3rd copy of the original list, so I'm actually sending the function the same random list that the others got. I'm not ruined by mutable variables. Also important to note is because of the way recursion works. Remember, every time you recursively call, you push a new frame on the stack. When that recursive function ends, you pop it off. You only come back to the main program when everything is done. So this, line 143, will terminate when the entire list is sorted, when all of the recursive calls have ended. This is truly a start-to-finish measurement. I'm going to print the list again to show that it's sorted. I'm going to print how many recursive calls it took and how many comparisons there were. And then at the end, I'm going to calculate the bubble end minus bubble start, selection end minus selection start, quicksort end minus quicksort start, and I can compare in seconds. So with that said, let us now run our code. How many numbers will be in the list? Now, in this first case, I'm going to be simple because this can get quite, I've got a screenshot of how much this can blow up. But I'm going to have 100 numbers in the list. With 100 numbers in the list, you can see that bubble sort had 4,950 comparisons, okay, and 2,639 swaps. And this is my list properly sorted after we're done. So I know my algorithm works. I know I get back a properly sorted list. In 4,950 comparisons and 2,639 swaps. Selection sort had the same number of comparisons because of the way I wrote the algorithm, 4,950. But I only had to swap 93 values rather than 2,639. You might think this resulted in less elapsed time. And you would be right. We'll see in a minute. Again, I printed out the sorted list, the results of selection sort. And you can see that just like the other, just like bubble sort, I get back a proper list with the same values. I'm truly doing as fair a comparison as I can. This line is from the print the third list. This is the result of quicksort. So this result of quicksort, this result of selection sort, this result of bubble sort all give me back identical sorted lists. So the algorithms are working properly and we're getting a fair comparison. Now, quicksort, you'll notice, to sort this 100 element list had 133 total recursive function calls. That may seem like a lot. It may seem weird that there are more recursive function calls than there are elements in the initial list, but if you think about it, that actually kind of makes sense because you keep calling until you get down to one element in each list. And I had a grand total of only 960 comparisons. I'll make 960 comparisons as opposed to 4,950. So here we see a huge difference. And that's going to tell in our time signatures. In seconds, bubble sort took only 3 1,000ths. Okay, small, trivial. Selection sort was much faster. It was almost half the time, 1.5 1,000ths of a second. The difference, 93 swaps versus 2,439 swaps. Selection sort is faster. But it pales dramatically in comparison to quicksort, which was almost 10 times as fast as, which is significantly faster than selection sort. Even with those 133 recursive calls, I still wound up with something that was faster. Okay, that's 100. Let's try this again. And this time, we're going to say, well, what happens with 1,000 integers in the list? Okay, we can see that the lists come back sorted. The next time I run this, I will go comment out those lines, print the lists, but they work. Bubble sort took 499,500 comparisons. We talked last time about bubble sort taking approximately on the order of n squared operations to sort a list of length n. So n is 1,000. N squared, 1,000 squared is 1,000,000. 10 to the third squared is 10 to the sixth. It's 1,000,000. 499,500 comparisons plus 254,000 swaps. That's about a little over 3/4 of 1,000,000. That's on the order of 1,000,000. That's a reasonable approximation. So we can see what we mean when we say that bubble sort takes approximately n squared operations. Okay, sort of kind of 1,000,000, 3/4, but close enough. For selection sort, it's the same 500,000 comparisons, less than 1,000 swaps. Okay, that's pretty good. That's a lot faster than bubble sort. But again, it's on the order of n squared. It's half of n squared. It's half a million out of 1,000. Quicksort this time, 1,000 elements, 1,349 recursive function calls. Those are going to be expensive, but you'd be surprised what the difference is. I only had to make 12,000 comparisons. 500,000 comparisons, 12,000. Now you see why it's called quicksort. Okay? 500,000, 12,000. Even with the overhead introduced by 1,349 recursive function calls, what we get is something that is significantly faster. Bubble sort, 0.377 seconds, almost 4/10 of a second. Selection sort, about a third of that, 0.14. It's between a half and a third. Quick sort, again, 0.007. Okay? Only 5%. Quicksort took about 5%. In other words, it ran basically 20 times faster. For a list of elements, Quicksort ran 20 times faster on my computer than did selection sort. And it ran almost 50 times faster than did bubble sort. Now, when you think about that, there's a reason it's called quicksort. Now, acknowledged, there is some randomness. There is some probability involved here, especially with quicksort. I mean, how good is our guess at the pivot? Yes, we could be incredibly unlucky, and the pivot that we pick in quicksort could be horrible, and everything is greater or everything is less, and we never split the list. That's not likely. In reality, you're going to get results like this. We're going to try one more larger number. We're going to run the algorithm again. And now instead of 1,000, we're going to sort a list of 10,000. Before I do that, though, I said I was going to go back and I'm just going to comment out the print statements that print out my list of nums, because I'm convinced that the code works correctly and the lists are being sorted, and I really don't want to see a list of 10,000 numbers printed out on my screen. It's just not worth it. Given that, we will now come back and we'll run the code. Clear the cruft and rerun this. I want 10,000 numbers. Okay? When we run our list of 10,000, we start seeing this will take a few seconds. Okay, and we'll let this go. It shouldn't go too long. There we go. Let's see. While we're waiting for that to happen, I've got a screenshot of something I did earlier which we'll see if I can manage to share here. Let's see if we can make it work. Okay, we'll get back to that in a minute. We'll get back to pie chart here. And we see that we've run. And with a list of 10,000 numbers, 10,000 squared is 100 million. And for 100 million, we got, for a list of 10,000, we find that, in fact, bubble sort takes, if you put commas in here, 49,995,000 comparisons. And it took a whole lot of swaps, okay? 24,878,876 swaps to make bubble sort work. So again, we're talking 3/4 of n squared operations. 10,000 is n squared is 100 million. 49 million and 24 million, add them together, it's about 75 million. It's a little over 3/4 of n squared. It's on the order of n squared. It takes a lot to make bubble sort work. For selection sort, same number of comparisons again, 50 million. Only 9,993 swaps. I didn't have to swap every number. So selection sort is faster than bubble sort in general. It's not a horrible algorithm. It's just incredibly inefficient. Okay. By comparison, now quicksort took 13,285 recursive function calls. That's got to be massive overhead. That's got to be a lot of resources consumed on my poor little 8-year-old Mac to have 13,000 recursive function calls. But here's the nice part. It's only 165,000 comparisons. 165,000, 50 million. 50 million, 165,000. And what we see is that sorting a list of 10,000 randomly generated integers in bubble sort took me 53 seconds. Selection sort noticeably faster, only 19 seconds. Little more than a third. A third would be about 17 and not quite 18 seconds. This took a little over 19 because of all those hundreds of millions, or those tens of millions fewer swaps. Selection sort is much faster. But look at quicksort. It's not a second. It's not a tenth of a second. It's 8/100ths of a second. This thing took almost a minute. This one took 8/100ths of a second. Okay. So the result of this shows us beyond any and all doubt that quicksort is far and away, in almost every case, a better sorting algorithm than bubble sort and selection sort. So, what's the point of this lecture? What's the point of what we're doing today? The point of what we're doing today is that we've learned that for this important computing problem of sorting, why do we have to sort? We have to sort because it makes search efficient. Because once we do this, once we have something sorted, we can quickly get to, and this is finally what I was hoping to show you. We can get to quick solutions and efficient solutions to an important problem. What do you take away from these two lectures, yesterday and Monday and today? What you take away is, for these problems, you can write some simple, quick code that will solve it. But if you really want to get serious, if you've got a hard problem, if you've got something at scale, you have to think. I told you on Monday the algorithm Tonstoffel. There ain't no such thing as a free lunch. And there ain't no such thing as a free lunch. Okay? If you want the best algorithm for sorting, it's complicated. If you want the best algorithm for searching, it's complicated. But with study, with analysis, with understanding, with figuring out good algorithms, comes an incredible performance. Now, the thing I'm showing you now is a screen cap of what I recorded earlier when I ran this. And for reasons unknown to most people, I wondered how long it would take if I had 100,000 elements in my list. Okay, 100,000, 10 to the 5th, n squared is 10 to the 10th. 10 to the 10th is 10 billion. And if I'm counting correctly, this is taking 4,999,000, or try this again. 4,999,950,000 comparisons and 2,497,532,109 swaps to do bubble sort. That's an incredible amount of work for this poor little computer. Selection sort has the same number of comparisons, but only the 100,000 swaps. It turned out that randomly, that particular algorithm, the smallest number was never already where it should have been. Quicksort took 128,375 recursive calls. That's a lot of recursion, 128,000 calls, but it only took 2 million comparisons. 2 million, 5 billion. A factor of more than 1,000, and that shows when you come down to it, the bubble sort algorithm took me 1,733 seconds. Okay? Quick math, a half hour, 30 minutes is 1,800 seconds. This took me almost a half an hour to run on my computer to do bubble sort with 100,000. Okay, 29 minutes basically. I'm not going to run this on this computer with 1 million elements in the list because you can then figure out how much more that's going to make it. My computer will give it up and die before it solves it. So almost half an hour to do bubble sort for 100,000 on this computer. Selection sort, 1,000 seconds. 1,000 seconds is about 17 minutes. Okay, 17 minutes is 1,020 seconds. This took 1,029. So 17 minutes and a little bit. Quick sort. We're still not at a second, folks. We are not at a second to do a quick sort. Quick sort took less than a second to do what this took almost half an hour, 29 minutes, and this took 17 minutes. That's the scale you get when you start writing intelligent algorithms. So, takeaways. Searching is an important problem. Because we need sorted lists to search efficiently, sorting is an important problem. The quick and dirty and simple and easy to explain and understand sorting algorithms are very inefficient. You don't want to use them for real serious problems at scale. The best that we've studied is quicksort. Selection sort and bubble sort are nice algorithms that are easy to understand, and if you're only sorting a few thousand things, yeah, who cares, do it. It's not a big deal. But you certainly don't want to start doing lists of millions or billions or trillions with bubble sort and quicksort. You will not ever get it finished. And with that, I will go ahead and stop the lecture. Thank you very much.